Hey guys, Mr. Middleton here. Today we're looking at interpreting graphs notes. At the end of this video, you should be able to interpret graphs by describing what is happening at each section of a graph, and you should be able to analyze situations and sketch graphs to represent a given situation. Okay, each graph has two axes, an x-axis, which goes left to right, right to left, however you want to look at that, and a y-axis, which goes up and down. Okay, and each of those has a label. Typically, the x-axis is labeled time. Okay, and the y-axis can have a variety of labels. Okay, so we're really jumping straight into an example here. It says, use the graph below to answer the following questions. Okay, so we're looking at this graph with sections labeled, or the axes labeled for us, and sections also labeled for us too, telling us what's happening. Also notice the title. Okay, what is the graph showing? It is showing the height of a plane over time. Okay, and I say height because that's usually what I use, but they labeled it altitude and over time because that's what the x-axis is measuring here. Okay, where is the plane at its highest point? Okay, and so as we look, it's at its highest point here. Okay, it's at its highest point at the cruising altitude. Where is the plane going the fastest? And so as we're looking at this, you might be tempted to say, hey, the plane's going as fast as here because this is the highest. Okay, but as we look at our graph, it's measuring altitude and time. Okay, and so this information is not on the graph. Okay, so we really can't answer this question. Always important to know what our graph is measuring. And every question can't be answered with every graph. This one is one that's, we can't. Okay, we're given the height, not the speed. Okay, number 4, what does the flat portion of this graph represent? And depending on what the axes are measuring, the flat portion will mean different things. In this case, the axis is measuring altitude or height. So when our graph is flat, what's happening is we have a constant altitude. This is a time where our plane is not going any higher or any lower. Okay, so it's a constant altitude or constant height. All right, another example says, use the graph below to answer the following questions. What is the graph showing? And here we have total distance over time, title, a commute home. So the distance for a person's walk home. Where is the person going the fastest? Okay, so as we look at this graph, again, it's not really measuring speed. So we can't just say it's going the fastest based off of like the highest point, but we can get speed by the slope of this line. Okay, so here the person's walking, okay, and here the person's taking the bus. Okay, and so we can see here that this distance is increasing a lot faster when the person's taking the bus than when the person's walking. The flatter the line, the slower the person here. So kind of a flat line here, kind of a steep line here. Okay, so when the person is on the bus, okay, and because that's where the line rises quickly or the fastest. And really the better to say it's the steepest. Hope that's a word. Okay, what does the flat portion of this graph represent? Well, in this case, what are we measuring? We're measuring total distance. Okay, so if it's flat, that means the distance isn't changing. So constant distance, or I'll say standing still. And as we look at the label for that section, waiting for the bus. Typically, if you wait for the bus, you're standing still. You're at a bus stop or something. Why does this graph never go down? okay? And as we look at what the graph is measuring, it's measuring total distance, okay, in this travel. Okay, so the total distance the person walks can never decrease. Okay, whether they're going to their home or drop something and had to go back, the total distance they travel will stay the same. Or not, sorry, will increase. It will not decrease. So that's why the graph never goes down. All right, moving to the next page. It says, use the graph below to answer the following questions. So we have weekend temperatures, and we're given temperature and time. What is this graph showing? Okay, and this graph is showing the temperature over the weekend. Okay, abbreviate weekend. Okay, which day was the warmest? And so as we look at this, it seems that this is like night or early morning, afternoon, night, early morning, afternoon, night. And so which day was the warmest? The first day. I don't know if that's Friday or Saturday, so I'm just going to say the first day. I don't know how you count your weekends. Okay. Which season is being shown here? It looks like it's a lot hotter here and a lot cooler here, so you might say like, oh, this is fall, but that could happen in the spring. It could actually happen in the winter too. Okay, we really don't know. If they were giving us like, hey, this is 90 degrees, we could say like, oh yeah, this is the summer, but they don't give us that information. They just say like, temperature's up, temperature's down. So I'll say not enough info. Temperature can fluctuate like this in any season. So we can answer that question right now. All right, it says, answer the question from the given graph. So they give us this graph, and before we start, make sure that we understand what the graph is measuring. The y-axis is measuring speed, how fast something is going. The x-axis is measuring time. And then the title is inline skating after school. So, which scenario best fits the group? Billy skates up a hill, maintains the speed for a while, and goes up a very small hill, only to quickly descend down a very steep hill. Then he goes up a smaller hill and finally comes back down to the ground. Okay, so here we go. This is not the right graph, and this is how we can tell. Remember that we're measuring speed. Okay, so imagine going up a hill. Okay, if you walk up a hill, run up a hill, something up a hill, it's a lot slower. Okay, and so as we look at what's happening here, it says Billy skates up a hill. Well, his speed wouldn't be increasing like really fast. He'd be going really slowly. You would expect it to go like he's going up a hill. It's like really trekking to get up there. Okay, so A's out. Okay, we're expecting something here that makes it so he's going faster. Maybe going down a hill would be more apropos or appropriate. So Billy slows as he goes up a hill. So again, he's not slowing down. He's speeding up. We want to eliminate this one right here. Okay, but I'm going to take this time to just encourage you to not get tricked by the visuals of the graph and them trying to make it so that it goes with that. So the whole trick of this is like, I'm telling you, he's going up a hill because you see the graph creating a hill. Okay, again, very important that you understand what's being measured. So see, Billy skates down a hill. That will increase his speed. Maintains his speed for a while. Yep, that's what that flat line means. Then picks up the speed, okay, before coming to a sudden stop. Yep, really fast or really just stopped, really, because that means time is at zero. Our speed is at zero. He then increases the speed again, and it's constant for a while, then slowly comes to a stop. And this makes the most sense. Okay, so see there. And then the last one, I will want you to follow the link on the agenda and sketch two graphs at the top, thrill, dragster at Cedar Point. The first should show speed of the dragster car over time, and the second will show the height of the dragster cars over time. Okay, so let me help you out. You should set these up similar to this, both big L's. Okay, and since they're both over time, this x-axis is time. Okay, first one, let's measure the speed of the dragster car. And the second one, let's measure the height. Okay, and I'll link that video there so you can watch it, kind of take the virtual experience and then graph these, and we'll talk about making sure we're good. All right, see ya.